So we've been talking about fuels, different fuels, and how much energy we can get out of them, and how we can transfer heat energy to different forms of energy that are more useful. And we recognize that the major sources of energy right now are coal and petroleum, and that there are limited supplies of those fuels. So eventually we will run out. Plus there's problems with pollution and the dangers of the fuels themselves, just extracting them from the ground and whatnot. And so we'll wrap up this unit, just talk a little bit about that issue of the limited amount of fuels and what we can do to either use less fuel or use different types of fuels. So one of the problems, other than just the fact that it's that these fuels cause pollution and can be dangerous, but right now in the United States we depend on other countries, and we and they are running out of supplies. So there's a lot of potential solutions. Some of them take a lot of money, some take energy to make different types of energy, some are controversial, but no matter what, it's all going to cost more money, and as a society we're going to have to decide what we're going to do to supply our energy needs over time. Now, one thing that can be done and is being done in certain areas is to produce synthetic gasoline, because gasoline is petroleum is what we use the most of right now as far as the fossil fuels go, and largely for getting goods and products and services and people moved around the nation. And so the way one way you can produce synthetic gasoline, synthetic means to make, not the gasoline that we would distill from crude oil. But in this type of synthetic gasoline, what you do is you take coal, and this carbon stands for the carbon from coal, and the coal has been treated somewhat to remove some of the volatile compounds and some of the other minerals from the coal, so it's been treated a little bit, and then you mix that with steam. This is water in the form of gas, so this is steam, hot steam, hotter than very hot steam, and you react that let it react, and you end up making carbon monoxide gas and hydrogen gas. And sometimes together this is called water gas, because it's made from putting steam over the solid carbon from coal. Anyway, once you get this so-called water gas, carbon monoxide and hydrogen gas, then that gas can react together in the presence of a catalyst. You have to have a catalyst present for this to work. In the presence of a catalyst, and the catalyst is going to be an iron or cobalt solid catalyst, iron or cobalt. Anyway, and then you bring these two gases together in the presence of a catalyst, and you can make alkanes of various chain lengths. Remember, alkanes are hydrocarbons with all single bonds, and so so they have varying chain length, and then also water. You produce the water back again, so in the form of a gas, because it's all hot. So you're combining the hydrogen with the carbon and with the oxygen to produce these alkanes that then can be used for gasoline. And as it turns out, this particular method of making gasoline is a very viable method. It's used in countries where coal is really cheap and plentiful, and petroleum is very expensive and not plentiful. For example, 40% of the gasoline in South Africa is made this way. Okay, so they don't have a cheap source of petroleum, but they do have a cheap source of coal, and so this is how they meet their gasoline needs. All right, now I want to speak for a minute about catalysts. We've mentioned it several times, but we haven't really talked in detail how a catalyst works, and it'll come up again and again as we move through next semester. So I'll just take a minute to describe briefly how a catalyst works. Okay, if you look at this particular diagram, this is what we call a reaction pathway or a reaction path diagram, and we've seen something a little bit like this before, where we said, okay, this would be an example of the reaction path for an exothermic reaction, because the potential energy of the reactants is up here and the potential energy of the products is down here. So this difference in where the reactants were and where the products were would be considered the heat of the reaction. This is how much heat energy would be given off when we go from reactants to products. Okay, so this would be the heat of the reaction. Sometimes we abbreviate that with delta H. Sometimes it's called enthalpy of reaction or heat of reaction. Okay, and so what you'll notice here is this pathway, if we're proceeding through this pathway and this green line is giving us an indication of the energy of the reaction and all the reactants and products going from the beginning to the end, you see that it goes up to a higher potential energy state before it makes it back down to the products. Okay, and so what this higher energy state is, or the amount of energy it takes to get to the top of the hill, if you will, from where the reactants start, this distance right here, this energy distance, is called the activation energy. And as it turns out, most reactions need to pass through the activation energy before they make it to the products, because remember, it takes energy to break bonds. Energy is released when new bonds are broken. So a lot of times you got to get the thing started, get some bonds broken or get the compound to start coming apart in some way in order for it to move towards products. And so that's the activation energy. And this sometimes is called the activation energy barrier. It's got to get over the barrier to get onto where the products are. And so what happens then is for a regular reaction, say the reaction that we were just talking about, the carbon monoxide combining with hydrogen gas to give alkanes of various lengths and water as products, to get from those reactants to those products, it's going to take some energy to break these bonds. And then more energy is given off as the products are formed than it took to break the bonds. But anyway, it takes a substantial amount of activation energy. But if you add the catalyst, the blue line here is the reaction path for the catalyst. And what a catalyst does is it allows an alternative reaction path that has a lower activation energy. And so this one, there's two little bumps here for some things that are going on in the presence of the catalyst that would not go on in the absence of the catalyst. And so your activation energy is smaller, and so therefore the reaction will proceed more easily to products. And in this particular case, let's say the catalyst that you're using is cobalt. And what happens is the cobalt, for example, the carbon monoxide may adhere to the cobalt or bind slightly to the cobalt. So say the carbon monoxide has a Lewis structure like that, it's got a triple bond. So if it might have some sort of bonding to the carbon monoxide, which will then weaken the CO bond. And at the same time, the hydrogen gas may also bond to some other cobalt. It will weaken this HH bond, and then you'll have a free hydrogen and a free hydrogen, which are very, very reactive, that are free to react with the water and free to react with the carbon. Also, when the oxygen comes off, if you have got a lot of carbon monoxides bound, then the carbon-carbon bonds can form. Everything happens more easily because the strain that's put on this carbon-oxygen triple bond weakens that triple bond. So it allows an alternative path. If the cobalt or iron, whatever catalyst you use, is not present, then this weakening of the bonds cannot occur, and so you're going to have to overcome the activation energy, and normally that means by adding a lot of heat energy, which in some cases is impossible, or some cases it's just not economically feasible to do. So in this way you can allow the reaction to proceed relatively cheaply, energetically speaking and financially speaking. So it's an alternative way to produce gasoline using a catalyst. And this is the reaction pathway. This distance from where the reactants start up to the top of the curve here is called the activation energy, and that's the amount of energy it takes to overcome the stability of the reactants to get it to move on to the products. And in the presence of a catalyst, the activation energy is less. Okay, so that's just an example of some details of how one can make synthetic gasoline, and it is done in many places.